All right, fantastic. Happy Friday. Happy nearly the end of October. This year is really getting away from us. We are so excited to be having our last lightning talks of the year this year today. And we will get started just about on time so that we are not too far behind. We want to be able to give everyone as much speaking time as possible. We will be doing about 5 minutes per presenter, with a couple of moments for transition in between. And then we can ask any questions in the chat. And should have time for about one question after each presentation. If you would like to ask it aloud, any time that we have at the end, we will dedicate to additional questions and answers. Most of you have been able to see we do have 2 interpreters with us today who will be providing ASL interpretation. We're going to keep them spotlighted at all times, and we will also spotlight the speaker. I trust that everyone is sufficiently able to work with Zoom at this point that they can move around and change the sizes as needed. Okay, great. So I'm just going to ask people to volunteer themselves for presentation, starting first with Carolyn. If you want to volunteer yourself first, that would be generous of you.
Sure.
Great.
Great. Let's see. And I'll make this. Awesome. So both myself and Erin Maloney at the University of Ottawa, we are interested in the home math environment during COVID-19. So we're both trying to see who in this community might have relevant data. So the question is, have you collected data on the home math environment during COVID-19? And also just thinking about, have you collected data that looks at the shift to virtual learning and how that might connect to children's math achievement, and also how potentially how parents' math-related attitudes might relate to the resources that they're providing to children or the resources that they're relying on as they're supporting children's math learning, kind of anything that's connecting the home context to math during COVID. And it could be both before, during, and kind of in this almost, we're still in it, but we're not in like the biggest kind of struggle of it right now. So we do have some data. So I'm going to talk a little bit about the data set that I have, and then Erin can take over and talk about the data that she has and kind of what we're looking for. But for the data that I have, it was an online survey for parents, and then we also had a Zoom interview with the child. And this was with kind of 2nd, 3rd, and 4th graders. So a bit of a range there in ages. And this was collected in March 2021, so a little bit after the beginning of the pandemic there. And it was in the United States, so here just around Virginia. So we collected some demographic variables of the children's gender, parent gender, and parent education level, things like that. We also collected math attitudes, so children's interest in math, their value of math, and kind of their competence. So those 3, as well as math anxiety. We also had parent report of children's math attitudes and parents' own math attitudes. We also had a few items about kind of mindset in math. We also collected some measures of children's own problem-solving performance and their calculation fluency. And then we had some specific questions about the parents' experiences in supporting their children's math learning during COVID. So did they, were they helping children more with their homework, or about the same, or spending less time, and just rating kind of how well they thought that they could support their children's math learning online, all of these things that kind of related to children's learning during COVID. Now Erin can talk about her study.
Okay, so in a very informal conversation, Caroline and I realized that we had probably very similar data sets, or had at least asked similar questions. So in our lab, we are really interested in understanding, so Caroline, because you've got control, can you just click all of them?
Sure.
We'll just thanks. Okay, so we are really interested in understanding a lot about like homework interactions that might be happening, but really looking at the role that parents are having to step into, even more so than what they normally would be during the COVID pandemic. So we have an online survey that we did where the informant is a parent. So we don't have the child perspective in this one. We just have the parent or guardian perspective. They are parents or guardians of children ranging in age from 2 to 19. So, oh, sorry, okay, the host asked me to start my video. Is it okay if I do? So I have to get so close. Okay, I can do it.
That's totally fine. Sorry.
It's okay. So in order for me to see the screen, I have to get so close to it so everyone gets like super up close version of my forehead. So sorry, but so the data that we have was collected from May to July in 2020, and it was collected using Canadian population. So we measured demographics. So again, looking at things like age, gender, household SES. We also have questions on access to learning tools. So really trying to understand what types of resources the parents have in the house. And then parallel questions about math and language arts homework, really looking at the resources, the parents' perceptions of their children's attitudes, parental attitudes. So looking at things like anxiety, how frustrating they find the situation, how confident they are in being able to help their children in these situations, the frequency of the help. And again, really looking at parents' perspectives on sort of formal versus informal math and language arts readings in home. So that's the data that we have. And the reason we are telling you about any of this is that we want to work with you. So if anyone has data sets that you think are looking at similar sorts of issues, we think it'd be really interesting to try to get a sense of, how this pandemic has really influenced the math, the home numeracy, home math environment, really across the globe. So if you're interested, we'd be happy to combine data sets and see what we can make sense of. And if you are, feel free to reach out to either Caroline or myself. You can reach us either via our email addresses, or we're both fairly active on Twitter. Yeah, so we hope to hear from you.
Fantastic. Thank you so much. I imagine that during this transition time or throughout the talk today, we could have people reach out to them via chat as well to set up some online or offline communication. We're going to have Roberto go next. So if you could start your video and I can pin you, and then you should be able to start your presentation. All right, when you're ready.
Can everyone see my screen? Yeah, okay, perfect. Hi everyone, my name is Roberto Abreu. I'm a PhD student at Rutgers University in Newark, and I'm glad to have this opportunity to talk about our project looking at the relationship between parietal and hippocampal connectivity and math achievement in adolescence. And in the interest of time, I will omit some details of our study, but I'm really excited to announce that these details will soon be available in our recent publication at Developmental Science. Given the life course implication of mathability, there has been a great effort to understand the neural underpinnings of individual differences in math achievement. However, task fMRI have shown conflicting patterns. While some studies have found lower activity of key regions of math cognitions, like the intraparietal sulcus, other studies have found the opposite pattern. That is, lower mathability is related to higher activity. And one of the reasons of this possible conflicting results might be related to the challenge that studying math cognitions poses. One of them is developing tasks that are appropriate for populations of different ages and different performance levels. And to circumvent these difficulties, researchers have taken advantage of resting state fMRI methodology, and that this technique allows studying connectivity patterns between spontaneous fluctuations of activity across different brain regions while participants are at rest inside of the MRI scanner. For today, we're going to examine the intrinsic functional connectivity of two regions of the math cognition network. One of them is the intraparietal sulcus, a hub for number processing, and the other one is the hippocampus, a region that is involved in storing numerical facts. Participants were 31 adolescents, and importantly, for the analysis that I will present today, we use math IQ residuals as opposed to raw math scores to control for the high correlation between math and IQ that we observe in our sample. And the resting state session consisted of 10 minutes. When researchers first looked at the IPS connectivity related to math ability, what they found was that children with math disabilities show strong IPS connectivity with frontal and parietal regions. And these negative differences between the two groups have also been replicated in individual differences studies. Typically developing children with stronger connectivity have lower math performance. And in adulthood, there is also a relationship between IPS functional connectivity and math ability, but now we observe the opposite pattern. That is, adults who have a strong math ability, they also show a strong functional connectivity. And overall, these results suggest a developmental change in the relationship between IPS functional connectivity and math ability from negative to positive from childhood to adulthood. However, there is no report of the relationship between intrinsic IPS functional connectivity and math achievement in adolescence. Thus, we first ask whether IPS functional connectivity has a positive or negative relationship in adolescence. And to answer this question, we use an anatomically defined left and right IPS seats for our analysis, and we look at brain areas that were modulated by the IPS functional connectivity and math achievement. And what we found was two clusters, one with its peak in the right lateral occipital cortex and the other one in the left falciform gyrus. But more importantly, these two clusters show a negative relationship, suggesting that in adolescence, IPS connectivity and math achievement have the same negative pattern as in children. The second region we aimed to examine was the hippocampus, and past research has shown that hippocampal connectivity is related to learning gains after math interventions. Similarly, changes in the hippocampal IPS connectivity are also positively related with changes in arithmetic efficiency after an intervention. However, there is no study exploring the relationship between hippocampal connectivity and current math achievement. Thus, we ask whether the relationship between hippocampal connectivity and current math achievement is similar to the one observed in learning studies. To answer this question, We also use an anatomically defined hippocampal seat, and here we found two clusters, one with its peak in the left presental gyrus and the other one in the left insula. But more importantly, we also observed this negative relationship, indicated that in contrast to learning studies, higher hippocampal connectivity is associated with lower levels of math achievement. In summary, our results suggest that IPS functional connectivity in adolescence follow the same negative relationship with math ability as the one reported in childhood. Similarly, they also indicate that stronger hippocampal connectivity is associated with worse, not better current math ability. And finally, one outstanding question is whether the hyperconnectivity is due to a history of higher activity in children with low math performance or innate differences that in turn result in low math ability. And I would like to thank my advisor, Dr. Rosenberg, and our collaborators.
Awesome, fascinating work. Really love to see the diversity of methods and methodologies that are being used in the MCLS. If you have any questions for Roberto, please place them in the chat. We are going to transition to Ilaria. We'll be doing our next presentation. If you could start your video.
Ilaria, you're still muted. Thank you. Sorry. A habit of keeping it off. Maybe Ece Demir can join if she wants. This is a collaborative proposal. Let me see if I can find my buttons to present. Is it coming? Switch displays. Okay. I hope everybody can see everything. So it kind of connects to the first presentation, but here we do not have data. We actually want to create a collaborative project. So the idea is to study home math talk and early numerical abilities. Dr. Demir, Lília, and myself are both interested in this project, and we both actually need to reach hard to find populations. So we were wondering, maybe there's other people. So we know that parental talk and early academic skills have a relationship. A lot has been done for reading, literacy, and language, much less, but it's a growing field. It has been happening for math and numerical abilities. And Ece, do you want to say anything here that I might be skipping?
I think you covered everything well.
I covered. That's basically the big idea, is that we want to do a little more of what is happening with the language and reading research, with the math research. And basically we identified that there is limited diversity in the current population. For instance, I would be interested in studying deaf children that are raised both in ASL or orally using English. And for us, it's much harder to find oral deaf children because they're mainstream, they're around the US, they're much harder to find. We have strategies to reach deaf signing children because they tend to go to deaf schools or deaf programs. We might be able, through connections, to reach families who are signers. It's much harder for the other kind. Ece, you want to say who you're trying to recruit?
Sure. Yeah, so we have an interest in trying to access children who were born premature, and similar to Ilaria, more is known about very early premature kids, but we know less about children who are born late premature. So that's again a population we would benefit to recruit from collaborations, as well as I have interest in children with early brain injury. Again, this is a rare group, but they are theoretically very informative in our understanding of brain and numerical development. So that's why we have this call, yeah.
And maybe we imagine that there's folks out there who are interested in bilinguals that speak maybe Spanish and English, Chinese and English, or other languages that might also provide very interesting information on how numerical information is being taught in the home, or how the language itself might impact the acquisition of number concepts. So we also noticed that every study out there has a little bit of their own task, their own measures. Some focus on talks, some focus on activities and surveys, rarely both. So we would like to offer the opportunity to get together and think a little bit through of a number of tasks we want to do and kind of find a standard core of tasks. And then the good thing about COVID, because there was one good thing, we all became so much better at remote testing. So let's leverage this. I could be recruiting participants that fit your criteria or Edge's criteria and basically sending them over for her team to work with them. And the same thing would be for other people on the team. So this is basically the idea to leverage each other's network. When we send out our flyers, we probably reach a lot of kids and families that don't match our criteria, but probably match your criteria. So why do we just leave them there if you can test them remotely? The age range for now is roughly 3 to 6, but it would be up for a discussion if we want to tweak it a little bit. We would have a core standardized assessment and set of measures. Every group would, of course, be free to add their own specific question. Not everybody would be interested in assessing ASL knowledge, for example, but you might be interested in something else that is relevant for your specific group. We could do a pre-registered and open source shared database. I think this is already what's happening with Childless, less familiar, but they have a lot online already. I heard something. Okay. And then we could even consider to submit a collaborative NSF grant for instance, buying hotspots and tablets, compensation for families, all these things that might facilitate even reaching people who would live in rural areas, hard to reach with weak internet or maybe no internet. If you're looking into low versus high SCS, providing hotspots and tablets might be something you need, and that could definitely be something. I think NSF would be really interested in diversifying the population we test. So this kind of effort would definitely be well received. Ece, do you want to add anything?
Yeah, I really like the emphasis on hotspots, because in Iowa, where I am, we are trying to reach rural populations. And one thing we identified was really this limited access to high quality internet. They have the devices. So that would be another probably advantage for us to reach to wider groups in the US.
Yes. So you can reach us through our emails. You can tweet Dr. Demir. She's on Twitter, not me. We have websites that you can reach, and you can spread the word. If you know of a lab, someone that's interested, just reach out. That was short, I think. I don't know, maybe 2 more time. I'll stop sharing. On to the next then.
Thank you so much. I'm loving all of these calls for collaborative work. And I think that we can really do a lot to expand our science by bringing in a lot of different perspectives, different locations, and like you just talked about, access, sometimes difficult to access populations. So next we have Seon Kim. And I'm sorry to the interpreters, I did not send you her abstract, but that will hopefully be okay.
Hello. Okay. Sorry. Hello, guys. I'm very glad to be here to present my work. My name is Seon Kim, and I'm here to talk about the idea of the math orthography today. In the present research, we use the term mathematical orthography to describe the knowledge about how to read or write the mathematics according to the convention for using symbolic mathematics. So the reason why the math orthography is important is that these 3 representations on the graph formed the basis of the mathematical framework. So understanding the mathematical symbols will be the top priority task for students to solve the mathematical problems. So in order to see how math orthography is related to the math performance, The symbol decision task was developed by Gail Hadley as a part of her research. So Gail had insight that similar to lexical decision or the spelling judgment task, we could measure the individual's familiarity about the mathematical symbols. So she showed the participants a symbol string and asked them to indicate whether the symbol is conventional or unconventional. There have been a few research based on this symbol decision task, especially in last year. The Douglas showed the evidence for the relationship between the math orthography and the math performance. So they found out for young adults, the arithmetic and word problem solving is strongly related to symbol decision. So in this project, we decided to replicate the research in 2020 and extend the finding with a larger sample size and a more extensive set of mathematical measures. Also, we used the online research platform in this study. And then we focused on the same research question with the last study. So our main research question was to explore how math orthography is useful for understanding the individual differences in mathematical solving. So for this research, we recruited 189 students from the first year psychology or the cognitive science at the Carleton University. And then we divided participants into two groups according to their majors. So including the symbol decision task and the participants solved the various types of mathematical problems in this study. And we also included the backward digit span and the order judgment task as a control variable. For the data analysis, we calculated the sensitivity measure of the D prime score for the math symbol task, for math symbol decision task. And for the arithmetic fluency, we used Lisa scoring. And for the rest of the math outcome measures, the rational number algebra and a word problem, we use the proportion of the correct response. So first, we look at if there is any correlation between the SDT-Math and these four mathematical outcomes. So as you can see on the table, SDT-Math performance was correlated with all kinds of numerical measures. And then in order to try to understand that the math orthography uniquely contribute to individual differences in adults' math performance, we performed hierarchical multiple regression for the symbol decision task. So I only brought the partial correlation numbers from the final model of the regression. So after controlling for the working memory and order judgment, as you can see on the right side of the table, we confirmed that the SDT-Math was a strong predictor, which account for the unique variance in mathematical measures. So in summary, here are two takeaway messages for you today. So first, we found a consistent pattern with the previous study that the SDT-Math predicted the unique variance in mathematical measures. So we can prove that the SDT-Math is a very useful assessment for understanding the patterns of individual differences for their mathematical skills. So even though the mathematical orthography is only a small portion of the math related skills, we believe that the teaching math symbol is very important part of the mathematics education. So hopefully our study makes a step forward to understanding the math symbol knowledge. Thank you for listening.
Wonderful. Thank you so much. So next we have Lília Marcelino will be presenting. So I will spotlight you once you start your video. After that, we will have Ludovica and then Vanessa.
Okay. Hello to everyone. I'm very glad to be here and listen some works with deaf children. That's a part of our project, not just with children with special needs, but the GBL project was the main purpose was to analyze the impact of a video game for deaf children. So here I will present just some data, because with COVID we lost our sample, our 28 children. Yeah, or we lost we lost our sample because of the conditions, technological conditions that deaf children have at home. So they don't have any computer or ways to support and continue the project here in Portugal. So we had to find out a new sample, a convenient sample, and I will just show you some results of that sample. Unfortunately, it was not the initial one, but we have 3 deaf children included in our sample. So this is the video game. You can see the final version at the link both indicated is in Portuguese, but this trailer I'm not going to show now because it's just 5 minutes the trailer, so it's the time of the communication. But I can put the trailer on chat if you're interested in watching. So why deaf children? Why mathematics specifically? Because most of the studies show that basic arithmetic is important predictor for later school achievement, and also improving numeracy. Is the impact of a low numeracy is a negative impact in society in general. Anyway, included deaf and hard of hearing students. Systematic literature reviews show that a delay in mathematics achievement in deaf and hard of hearing students comparing with hearing students shows that specifically low performance in abstract counting, symbolic addition, and subtraction. Why in the educational video game? Especially because game-based learning approach really significant and positive influence in several areas of cognition, including areas of knowledge as mathematics, and also in good game-based learning approaches the players and students are engaged and immersed, and learning is about to be engaged in a task also. So the main problematic is what I already said. The participants are deaf and hard and hearing students between the grade 4 to 9 attending public school. One of the deaf children was home education, because the mother thought that it's not enough. They don't have the attention that deaf children needs at school. So we prefer to give all the 4 years of the first 4 years of schooling at home, and he passed the national exams with a high score. So the mother made a very, very good work with him. And all the children, the special to attend the public school. One of a young girl, one of our participants, has a special curriculum because she has syndrome. Gallaudet syndrome is a severe type of epilepsy, can give some cognitive deficits. The main goal is to explore the research-based educational video game to support mathematical learning, especially basic arithmetic and basic geometry. So, 2 research questions. Did students progress in mathematics have to play in the video game? Is the gameplay of this video game an engaging experience for players. So as I said, the pandemic, the video game intervention and the field work to measure with our initial sample was impossible. Instead, this convenient. And the video game here was used in a different way. Was not just the measure mathematics achievement and then play the video game and measure again, but using the levels and the game challenge as a training program, as a tutor. So use each of the levels, nível 1, nível 2, nível 3 means level 1, level 2, level 3, of each game challenge. Game challenge, addition and subtraction, 1, multiplication and subtraction, 2, and a kind of turtle game that is to stimulate algorithm thinking and calculation with angles, the challenge 3. So what use is a kind of clinical contest, and respecting the learning pace of each children, the level of each children. We use remote sections in school contests and also in family contests. So this is our sample. If, as you can see, there are different special needs, deaf without cochlear implant, and some children, deaf children with cochlear implant. Dyscalculia, this boy with home education, and another children deaf with cochlear implant, and other child with Asperger's syndrome was the only one who showed a progress in mathematics achievement. The rest did not. So in general, the results don't show a difference between before and after playing the video game. But maybe the conditions of evaluation and intervention, the instrument itself, the family versus remote sessions, the learning pace of each child, the number of game sessions was between 10 and 12, was very, should be more than 12 sessions for this kind of children with this kind of special needs. May explain the results. So this, at the moment we are analyzing the arithmetical strategies used by each child to solve each game challenge. So we are analyzing now qualitative data observation. But a second question is the gameplay of the video game and engaging experience. Yes, all children reported feeling more intensity in positive emotions than negative. Like I like the game sessions. I'm feeling satisfied, enthusiastic, involved in game sessions. As a final consideration, more qualitative and ecological analysis and supplementary studies are necessary to consider the video game as an effective tool to improve mathematical achievement in deaf and also hearing children with special needs. Thank you for your attention.
Fantastic. Thank you so much, Lília. If anybody has any questions for Lília or for any of the other presenters, please feel free to drop them in the chat. I am now going to spotlight Ludovica. Once she turns on her video, and I will spotlight Stacy. Wonderful, fantastic. Let's get going.
Okay. Can you see and hear me? Normally should be working. Okay. Hello, everybody. I am Ludovica Veggiotti from Paris University. And today I'm glad to present a study that aims to investigate number and action mapping in human infants. So humans and non-human primates and many other animals share the ability to rapidly extract and compare the numerosity of sets of objects in an approximate fashion. This ability is also known as the number sense, and it is supported by the approximate number system. The neural basis of this system, the ANS, has been found in the parietal cortex, in particular the human intraparietal sulcus. Critically, this area is involved in many functions beyond the domain of numerical cognition. For example, spatial and action-related aspects of perception, multisensory and sensory motor integration. Moreover, it has been shown that adults present effects of interference when simultaneously processing numerical information and action-related information. For instance, they are quicker in opening their hand in response to large numbers and in closing their hand in response to small numbers. All these studies lead to the idea that numerosities and action are connected in the adult brain, but still little is known about this link during development. So the current study constitutes the first attempt to investigate the presence of a link between action and numerosity perception in 7 to 9 month old infants. So 40 infants were habituated with an image of a set of dots with different numerosities, and simultaneously, as you can see, an image of a hand that showed different opening positions. In the habituation phase, half of the infants observed the congruence between action and numerosities, like large numbers paired with an open end, while the other half observed the incongruence between them, for example, small numerosities paired with an open end. In the test trials, infants were shown with both congruent and incongruent pairings. So an ANOVA with an habituation condition congruent versus incongruent, and first test trials versus the second as the between subject factors, and the test trials congruent versus incongruent as within subject factor showed a significant interaction between habituation and condition and test trial. In conclusion, in line with previous studies, only infants habituated to a congruent mapping between action and number show evidence of learning the rule and apply to new examples during test trials. These findings show that infants spontaneously associate magnitude-related changes across the dimensions of number and action-related information, offering support to the existence of an early proverbal number-action link in the human mind. So I would like to thank you for your attention, and thanks to Lola Devi and Gisella De Carli, who are my collaborators, to the ENCC Baby Lab, and to the babies that are so important. Okay, I'm done. I stop presenting, and someone can go ahead if you don't have questions.
Awesome, fantastic. I love that novel approach to studying approximate number system acuity and recognition. Would love to see more of that, and would love to see a video of it. So I am going to spotlight Vanessa and Jen.
Okay, give me 1 second. I have everything loading up just real quick. Oh no. Let me stop my video real quick. See if that helps. Oh, of course. My computer froze real quick.
Vanessa, do you want to hold on until the last one and we'll have Serena go next while you try to get your computer working?
Sure, we can do that.
Okay. Serena, are you ready to go?
Yes.
Wonderful.
Do you hear me? Okay.
We can hear you. I will spotlight you.
Okay.
All right, thank you.
Okay. So, hello everyone, my name is Serena Dolfi and I am a PhD student at the University of Padua. And today I will briefly present some of our investigation regarding numerosity perception in developmental dyscalculia. So just a brief outline of the framework. We are interested in the basic ability of estimating the elements in a set or judging which between two sets as more elements than the other. And the mainstream theory, the approximate number system theory, proposes that the precision in these discriminations are reflecting the quality of an internal representation of numerosity. And many studies show that the performance in this type of task is also predictive of later mathematical learning, so that an imprecise approximate number system has been proposed as a core deficit of developmental dyscalculia. We now know that the persistent deficits in mathematical skills are much more heterogeneous. However, several studies have individuated at least clusters or subgroups of children with mathematical difficulties that also present deficits in non-symbolic numerosity. And from recent, in recent years, we have also become more and more aware about the fact that when we are performing this kind of task, we are also influenced by other characteristics of the stimulus, like, for example, the congruency or incongruency with other perceptual cues. And recent evidence has also suggested that children with developmental dyscalculia may suffer more intensively from this interference from other perceptual cues, which is interesting and particularly relevant in the discussion regarding the role of domain general mechanisms, like, for example, inhibition in the development of mathematical skills and in particular mathematical difficulties. So our question was to investigate the interference effect in developmental dyscalculia to try and understand if a deficit non-symbolic numerosity task could be indeed associated with a stronger influence from non-numerical cues. And if so, if we could individuate specific non-numerical cues that would be particularly relevant for children with difficulties in mathematics. To do so, we tested a large group of children between 8 and 14 years old, and we selected a group of 40 children with a poor mathematical performance based on the Italian battery for developmental dyscalculia, and we matched the control group with average mathematical skills, but with similar overall intelligence and visual spatial working memory skills. And all the children performed a classic non-symbolic numerosity comparison task. They were presented two arrays of dots and they were asked to decide which between the two has more elements. And the paradigm and the stimulus space that we used was inspired by the method proposed by Leuven and colleagues in 2015, which summarizes some of the perceptual cues present in the stimuli in two variables, size and spacing, one related to the size of the elements and one related to their spread in space. And we varied the ratio of numerosity, size, spacing orthogonally to then estimate their singular impact on the individual performance. So as for accuracy, we found a small but significant difference between the two groups with a lower performance presented by the dyscalculic group. And then we estimated the contribution of numerosity, size, spacing at the individual level, but then on top you can see the mean coefficients. And we found that the performance was overall determined by the numerosity information present in the stimuli, but that an effect of size and spacing was also significant, at least at a group level, for both groups, which indicated the presence of a non-numerical bias. On the bottom, you can also see the individual estimates that are plotted pairwise. Each dot represents a single participant, and the closest a dot is to a certain line, the stronger is the influence of that particular feature on the participant's performance. And we can see that the participants are pretty much aligned with the numerosity dimension, but that there is some variability along the size and spacing axis, which indicates the bias. And we can also see that the two groups are pretty much aligned and overlapping. And from the individual coefficients, we can also estimate the individual discrimination vector in the three-dimensional space, which offer a summary of the non-numerical bias as the angle between the discrimination vector and the numerosity dimension. So we compared the angles between the two groups, but we did not find any significant difference. And as for which specific feature could be mostly relevant, we computed the projection of the individual vector onto the individual feature lines. But again, even in this case, we found similarity across the groups, so that for both groups, the most relevant features were total perimeter and field area. But again, this was similar across the group. Instead, when we estimated the numerical acuity as the group refraction, we found a significant difference between the two groups with a higher estimate for the dyscalculic group, which indicates a lower acuity. So to summarize the results, we found a consistent difference in performance between the two groups that was, however, not associated to an increased bias in dyscalculics from non-numerical cues. And indeed, we failed in finding a specific or differential non-numerical cue influencing the performance of dyscalculic. Instead, we found a significant difference in the numerical precision between the two groups. And this is more in line with the idea of a difference in the numerosity representation compared to a difference in bias. And we know that these results are in contrast with previous literature, and we are currently trying to understand why. Especially, we are trying to understand what is what is the relationship between visuospatial abilities and this interference effect. And an open but interesting question is also whether the reliance of these numerical cues is indeed an interference effect, or rather a compensation due to a pre-existing numerosity deficit. So with that, I end my presentation. I thank all the people that worked on this project, and thank you for listening.
Fabulous. Thank you so much, Serena. I'm going to pivot back to Vanessa. Hopefully her tech is working a bit better. And Serena, if you could stop your video share, perfect.
Okay, can you guys hear me and see me okay? Okay, perfect. So my name is Vanessa Rosales Cerda, and I am a fifth-year PhD student in Dr. Nicole Wich's lab. And so the focus of our lab is to investigate the link between language and math cognition. And we use multiplication problems as a tool to investigate this link, since they're typically learned, through rote memorization and are thought to be stored as language-dependent memories. And I'm sure all of you remember rehearsing these facts, like 2 times 4 equals 8, or 6 times 3 equals 18, and so on until they're burned into your memory. But individuals who are bilingual are in a unique situation where they're typically rehearsing these facts in only one of the languages that they know. And so this causes many bilinguals to say that they can only do math in that language, the language that they learned the math facts in. And in fact, a consistent finding in the literature is that bilinguals are faster and more accurate when they're asked to perform arithmetic in the language they learned math compared to their other language. And so this finding is especially relevant for bilingual education, given that bilinguals are at a potential disadvantage, compared to their monolingual peers if they're being tested in their weaker language. So the focus of my dissertation is to determine if bilinguals are processing or simple arithmetic facts in the same way for both of their languages. And so to answer this question, our lab uses electroencephalogram, or EEG, and it's a continuous measure of electrical brain activity from the surface of the scalp. And so this technique is really useful in helping us understand how arithmetic processing unfolds over time. And so we measure brain activity while bilinguals are performing arithmetic in one language compared to the other. And specifically, we're looking for differences in brain activity, like differences in voltage amplitude of the response in one language compared to the other, or maybe like differences in timing across languages, in the brain response across languages, to really understand if there are differences in the way bilinguals are processing simple math. And so we have bilinguals complete the task that you're seeing in the top left, where we present two spoken numbers like 2 and then 4. And then we present a visual solution like 8. And we had Spanish English bilingual adults tell us, by a button press, whether 2 times 4 equals 8, yes or no. And half of the time we presented answers that were correct, like 8, but then the other half we presented answers that were incorrect, like 12. And so of course we measured their brain activity as they completed this task in their language of learning, or LA+, and in their weaker language, LA-, expecting to see differences in either the amplitude or the timing of the brain activity. And so here I'm showing the averaged brain activity from the moment that bilinguals saw the answer. And to orient you, I'm showing changes in voltage on the y-axis over time in the x-axis. And so the solid line represents the average response to every time bilinguals saw correct answers, and the dashed line is the average response to incorrect answers. And if you notice, there's a large difference between correct and incorrect answers at this point in time that I've highlighted. This is a P300. The difference is driven by a P300, and it's a well-studied response that indicates that adults are treating correct answers as targets. So adults have years of experience retrieving these memorized facts from memory. So it makes sense that they're showing this response in the language that they learned math. But surprisingly, bilingual adults show a nearly identical brain response in their other weaker language as well. So just looking at this data alone, we might be able to conclude that bilinguals are using the same cognitive processes across languages, since we saw the same type of response, a P300 in both languages, and they're doing this with equivalent efficiency across languages, since we didn't see any differences in the timing or the voltage amplitude. But we thought, okay, well, adults can solve these problems pretty effortlessly since they're simple multiplication problems. So what if we try to increase the difficulty of the task by speeding the pace at which the problems are presented? And so the goal, of course, is to increase the difficulty of the task, but promote delays in processing, especially for a weaker language. So we presented bilinguals with a nearly identical task, only changing the timing. And when we did that, we compared the brain responses between the original slower task and the speeded task. And so for LA+, so this is the language they learned math in, we did see a delay in processing where the P300 was about 80 milliseconds delayed for that speeded, more difficult task. So that confirmed for us that bilinguals did have a harder time with this task. And so we expected LA- as the weaker language to be even more delayed. But to our surprise, LA- is in red. It didn't elicit any additional delays for the speeded task. And so the responses were again nearly identical across languages. So even though we did increase the difficulty of the task, we didn't reveal any differences across languages. But in our task, we do present two different types of problems that I didn't mention. It's widely known that small problems involving small numbers like 2 times 3 are more practiced and easier to solve than problems involving large numbers like 9 times 8. So we decided to look at the brain response to our most difficult problems for our most difficult task. And so just for reference, when we looked at the smaller, easy problems, we didn't see any differences in the brain response for LA+ in black and LA- in red. And that's most likely because these problems are so practiced that they can easily be processed in both languages. However, when we look at the larger, harder problems, we do see differences in the P300 between languages, where adults are more able to detect solutions as targets in the stronger language LA+ compared to their weaker language LA-. So in conclusion, it would seem that our bilinguals are using the same cognitive processes across languages, since in all cases, they elicited the same type of brain response. And they're also processing these problems with almost equivalent efficiency across languages, suggesting that at least by adulthood, bilinguals can perform simple arithmetic in both of their languages. And it is only under the most difficult circumstances for the most difficult problems that language processing differences are occurring in the brain. And so with that, I would just like to thank all of my bilingual adults for sitting through hundreds of multiplication problems for me. And of course, my mentor, Dr. Wicha, and my Wicha Lab family for supporting my work. So thank you guys for listening.
Wonderful. Thank you so much. It looks like there are a couple questions for you, Vanessa, in the chat. If anyone has any other questions for any of our presenters today, now would be a great time to ask it. I realize that we are just over time. Timing worked out perfectly, but I think folks might be willing to and able to stick around for just a couple minutes. If anyone has any other questions, you can either converse live or via chat. Thank you everyone for a fantastic set of presentations today. It was really great to hear about such exciting new work coming up. And we look forward to seeing you all next week for our next symposium on Thursday.